Okay, so today I want to kind of, after just announcing a couple of things, I want to just pick up with where we left things off last time, which was linearizing systems of nonlinear differential equations and then analyzing the stability of the equilibrium based on that linearization. And so just a couple of things. Sorry about having to cancel the office hours on Thursday. Sadly, Cat Onyx is no longer with us, so I was dealing with cat stuff on Thursday. So sorry about that, but the homework is due on Wednesday, and I do have office hours tomorrow, so you do have a chance to catch me tomorrow if you have any questions. So those are from 1:30 to 2:30. The other thing I want to mention is I did send a message out to the listserv for the math majors, but I realize not everybody here may be a math major. So I just want to share that with you. So we've got an advising event going on Wednesday night. So I am the advisor for undergraduate programs. So here's the announcement for it. So just Wednesday, November 4th from 5 to 6 p.m. I'm going to just have a registration info event just to go over our different programs, majors, minors, certificates, and all of the courses that we're going to be, the upper division courses that we'll be running in the spring. So if you have any questions about course selection, math course selection in the spring, this would be really great to attend. And I'll record it and post it online for those that can't attend. But any questions about that? The link for the event is over here, and I did email an invite, like a Zoom invite to the math listserv, but if anyone would like a Outlook invite, you can just shoot me an email and I can send you an invite so that you can add it to your calendar. Okay. So yeah, so I want to just review the process that we went through last time and then give you guys a chance to practice them together before we move on to the next topic. So just so you know, we've got an exam 1 week from Wednesday. So our exam is next Wednesday, and that is going to cover chapters 3 and 8. The systems of differential equations, linear and nonlinear. And so just so you know, today and tomorrow, we're going to start material in chapter 6, or on Wednesday, but that stuff won't be on the exam. So that's going to be on the very last exam, which is going to be during finals week. And yeah, I guess that's the other thing I wanted to mention is that I also did post an announcement about when our third exam is going to be scheduled. And if you can check out the announcement, but it's the first Monday of finals. So Monday, December 7th from 11 to 1 p.m. That we can worry about after Thanksgiving. We can talk about that. But just so you know, that is not a final exam. It's just going to be on chapter 6. So it's actually going to be worth a little bit less than our previous 2 exams. I don't suspect it will take up the full 2 hours. So I'm going to write the exam to take about an hour and 15 minutes, maybe even less, but you're welcome to use the time if you like. Any questions about that? Yeah, so this would be through Jacobian matrices. Yes, there was a question about what is going to be the last bit of stuff on the exam. It's going to be exactly what we talked about right now. Okay, so let's see, what am I sharing with you? Okay, so I've got my iPad, great. So these are kind of the typical problems that you might have come across on the homework. So you have a system which is non-linear, and we want to go through a series of questions like find the equilibrium, linearize the system there, and then identify the type of stability of each of those equilibriums. So we did do this example last time, so I want to go through this rather quickly just as a sense of recapping this. If you have any questions, we did go through the steps way more carefully last class. But the idea here is, well, the first thing you'd want to do is find the equilibrium, obviously. So to do that, right, we would want to take and set both dx dt and dy dt equal to 0 simultaneously and solve that system. And in this case, there are two equilibria. So nothing new there. Okay, what's new is how we do this linearization process. So we need to do this at each equilibrium. And so the one we did together last time was at 1 minus 1. So what we can do is I'll kind of outline the calculus way of doing it, which is a bit longer, and then we'll talk about the linear algebra way of doing it with the Jacobian, which is the way I would recommend that you do these. But I just want to make this connection between those two methods. So when we're doing this the calc way, it's like finding a tangent line for a function, in this case, a tangent plane for a function of two variables. So we take our differential equation and we want to linearize this. So we would take the partial derivative with respect to x, that gives me minus 2x. I would take the partial with respect to y, which is 0 in this case. And then we plug them in to the formulas. We evaluate it at the equilibrium. So we need to do this separately for each equilibrium. So I would take 1 minus 1, plug it in here and get the slope in the x direction. If I had a formula over here, I would plug them in and get the slope in the y direction. And then we need to know the value of the function at that point, which should be 0 because this is an equilibrium. And then we've got our linearization, at least in terms of x and y. So again, this is sort of like this tangent line process that we kind of reviewed a little bit last week. But any questions about that? Okay, and after we've done that, then we can rewrite this linearized system in terms of u and v, which are going to denote like small variations away from the equilibrium in the x and the y direction. So I would take these values, plug them in. Each x I'm going to replace with 1 plus u. If I had a y, I would replace that with minus 1 plus v. And then we rewrite the linearized system in terms of u and v. So for the dx dt term, we would say, okay, we can approximate 1 minus x squared with this linear function. And now let me write this linear function in terms of these new variables u and v. So taking the derivative of this with respect to time tells us that dx dt is just equal to du dt. So I can replace this really easily with du dt. And then I want to replace each x and y. And so in the end, I should get something that has no constant term. If you have a constant term left or some nonlinear term, then that means you probably made a mistake along the way. So just be aware of that. Okay, and then we would do all of the same stuff for the other function. This case, the equation for y prime happens to be linear, so we should get back the same thing. But that might not always, it's not going to always be the case. But it doesn't look any different on what we would do for the other one, just the partial derivative. Since the function g of x is different, the partial derivatives are a little bit different, but that's it. And so when we ask for give the linearized system, I'm looking for a system of equations like this. This would be your box with your final answer, at least for that part. So these should be a system written with respect to u's and v's. There shouldn't be, or you can pick your favorite letter, but don't use x and y. We're now expressing this in terms of u and v. Any questions?
What would you call this answer that you just boxed?
That would be the linearization of the system at the equilibrium 1 minus 1.
Thank you.
Just one question on the du dt part.
Mhm.
I'm still a little bit confused where that's coming from. Are you just taking the derivative of that x equals 1 plus u, both sides of that with respect to t?
Yep.
Okay, all right. Okay.
Yep. So yeah, so u is just like a shift of x. We're just shifting it by 1 unit. So their derivatives would be the same. Yeah. But yeah, you can just think about that's an equation. We take the derivative, we do the same operation to both sides, differentiate with respect to t, then we're still going to get an equation left. Yeah. Okay. Anything else? Okay, so then the method that I would suggest you try and do would be this linear algebra approach, which would be using the Jacobian. So the Jacobian is a matrix of partial derivatives. So these would be partial of the first equation with respect to x, second equation, first equation with respect to y, and then g of x is denoting the equation for dy dt. We would take partials there. So these x and y stars mean we're going to evaluate them at each equilibrium. So what I would do, the information I would need for the Jacobian would be what is the partial of f with respect to x at 1 minus 1? And what is the partial of y at this point? So we need all of these partial derivatives in order to set up the Jacobian. And the nice part is we actually don't need any of the rest of the work there. So we wouldn't need to do any of this stuff down here. So, right, our Jacobian would therefore be the partial with respect to x at the equilibrium is -2. That goes over here. Partial with respect to y at this point is 0. So the 0 goes over here, and then -3 and a -3. Just keep in mind that if the problem asks you to give a linearization, this is not your final answer, right? This is the Jacobian. And from this Jacobian, you would go up to that direction, and still your final answer should be a system of two linear differential equations. So once you get the Jacobian, you need to know how that is equivalent to some system of linear differential equations. Any questions?
On the homework, I thought that we had to go through that whole like calc process, so I did it the long way. So I guess we could have done it with the Jacobian too. Oh.
Yeah, either way is good. So I would suggest, yeah, it's good to practice either way. I think the Jacobian is a little bit streamlined. Yeah.
Yeah. Okay.
Otherwise, yeah, you can go through that process and then get this system over here. And then you would want to set up the matrix of coefficients to look at the eigenvalues and stuff like that. So the Jacobian gives us exactly that matrix of coefficients. Okay. So then once we've got this, now it's the same stuff that we did with linear systems, and that's the nice advantage there. So now I would find the eigenvalues by setting the determinant of j minus, subtracting the lambdas from the diagonals. And here we could check that the eigenvalues are -2 and -3. And so if we have two negative eigenvalues, then what type of equilibrium is 1 minus 1? That's right. That is going to be a stable sink. That's right. So everything is going to close to that equilibrium, should head in towards that equilibrium. But keep in mind, this is not going to describe how solutions far away from this equilibrium are going to behave. So that's all we would need to say as far as classifying the equilibrium. And it's not asked on the homework, except for the last problem where you've got the rabbit and the foxes. But if you were to ask to sketch the phase plane near that point, then I know that at this point, 1 minus 1, things should be going in to that equilibrium.
So say it's a saddle point with a positive and a negative eigenvalue. Do we need to find the eigenvectors when we're graphing it, or can we just guess on the direction of the eigenvectors?
Yeah, hold on to that question in a second. We'll see something like that next. And from this picture, again, the thing I want to just stress is this doesn't really tell me anything about what's happening over here or over here or over here, because these are pretty far away. So it's just saying that if you start close to this, you're going to head back to that equilibrium. Okay, any questions?
You seem to be keeping everything vague when you say close, so you're not going to ask us, like, at this point, is it going to be in or out? That's not something that's going to be fair game, right?
No, that's right. Okay, so if we wanted to do this at the other equilibrium, that would be at minus 1, 1 was the other equilibrium. Let me just kind of show you what the work might look like if we're just using the Jacobian. Then we would just want to show, first of all, what are all of the formulas for the derivatives, partial derivatives. So that's given over here. And then we want to evaluate each of those at the equilibrium, which in this case is minus 1, 1. And so if these partials depend on x and y, then we're going to get different values for the derivatives, and we'll get a different Jacobian. So down here, we've got the Jacobian, and oftentimes, let me just say, that might be written as like a function. So this is telling us that it is the Jacobian at minus 1, 1. And the only difference here is we now have a positive and a negative eigenvalue. So that makes it a semi-stable saddle. Yeah, and so the question was, well, like, what should we do if we want to include that on the graph? And I don't think it's going to come up on your homework assignment, because most of them you just have to classify the equilibrium. But if you wanted to sketch this in the phase plane, then yeah, to be really careful, you could find the eigenvectors for each of these eigenvalues. I don't want to go through that process, but this is what they would come out to be. And so then when you're sketching your picture, we now have a separate picture of what's going on at the other equilibrium. And it is helpful to see the general directions of these, just to know which directions are going straight in and which is coming straight out.
So for the rabbit and fox question, the third question on the homework, there's you want us to graph it, and there's some saddles there. Do you want us to find the eigenvectors for these, or can we just guess? Not guess, but just yeah. So yeah, for that question.
Yeah, I think it would be good to go ahead and find the eigenvalues for that if you want to sketch it. It doesn't hurt to practice that, since that is going to be on the exam as well. So I think it's good to just review that anyway.
Okay, find the eigenvectors.
Yeah. Yes. Let me just remember that if I actually don't recall what the answer is to that rabbit fox one, but when you have complex roots, and I'm not saying that that's going to be the case, then you wouldn't find the eigenvalues, or excuse me, the eigenvectors, because we get these spirals or these center points. And so really what you would be interested in is, what direction are we rotating into the equilibrium, or what direction are we rotating around the equilibrium, as opposed to eigenvalues and eigenvectors. Okay, So any other questions about this? I do have one for you to practice, and sometimes you don't know if you have questions until you try and do them yourself. But if you're kind of curious what this picture of the phase plane looks like, let me share that with you. I've got that on another screen. Yeah, and so let me blow this up a little bit. Okay, that's not what I wanted to do. Okay, can you guys see that? Sorry if it's not, that'll work. So this is the what's called like a stream plot for this system. And what you can see is if you look over here, you can see this saddle-like behavior over here. And you can see kind of these directions of the eigenvectors as well. And over here at 1 minus 1 was this sink. So you can see everything is going into the point at 1 minus 1. And you've got saddle-like stuff going on at minus 1, 1. Okay, so here's the problem I'd like you guys to work on in some groups. We can see what sorts of questions you might have on this. So it's a different one than what's on. So this was worksheet 19, by the way, that we were working on last time. So this was the pendulum problem that I suggested you try. I'm gonna leave that as something for you to try. I wanted to have a system which has x's and y's mixed up a little bit more, so the partial derivatives and all of that is, you need to be a little bit more careful about how you do that. But here's the system, dx dt equals 4x minus 2xy. dy dt is 6y plus 2xy. And so the exercise is find the equilibrium, give the linearization, and then based on that, classify what type of stability each equilibrium point has. You don't have to sketch anything here. And my hint will be, as you're working on these, there are 2 equilibrium. One of them you can see very quickly is the origin, 0, 0 is an equilibrium, but there is another one. So you need to be a little bit careful about how you solve that system to find the other equilibrium. But there's 2, the origin and one other point. All right, I just opened up some breakout rooms. Please help each other out when you're working on these. Make sure you write this down before you head into your breakout room. And then I'll just circulate through and give you guys some help if you need it. Great, so let's kind of run through the process here. So I have the equilibrium written up, but we can go through the linearization process. Okay, so one way to think about the equilibrium is to take the top equation, factor out 2x, see, well, dx dt is going to equal 0 if x equals 0 or y equals 2. And just be sure that this doesn't mean 0, 2 is an equilibrium, right? This just tells me conditions that will make the top equation 0. And then each of those conditions we should check in the bottom equation. So checking what happens if I plug x equals 0 into dy dt. The only way that would equal 0 is when y is 0. So that gives us the equilibrium at 0, 0. And then we can check the condition when y is 2 to figure out what additional restrictions we would find from the dy dt equation. And that would give us equilibrium at minus 3, 2. Any questions about that part? That came up. Okay, so next would be the linearization. So if we want to find the linearization, then we want to calculate each of the partial derivatives. And then evaluate each of them at the equilibrium values. And that seemed to go pretty well. So f partial of this was 4 minus 2y. Partial with respect to y would give us minus 2x. Partial with respect to of g with respect to x would be 2y. And partial of g with respect to y would be 6 plus 2x. Any questions with that? So yeah, so then you could write out a general formula for the Jacobian if you like, which says that would be our matrix. And then at each equilibrium, we could evaluate each entry of the matrix. So at 0, 0, this gives us 4, 0, 0, and 6. Okay, which is diagonal. We can see the eigenvalues there, but you could go ahead and it's pretty quick calculation to get these two eigenvalues. So that would mean that at 0, 0, that would be an unstable source. And I should say, it asks for the linearization that would be the linearization at 0, 0. Any questions? Okay, then we could calculate the Jacobian at the other equilibrium. So let's see, here we get a 0 over here and a 0 over here. And this gives us a -2, -3, gives us a +6, and we get a +4 over here. And so looking at this one, we would have minus lambda times minus lambda minus 6 times 4 is 0. So lambda squared minus 24 is 0. So here lambda is plus or minus the square root of 24. So this means the linearization for this one, right, would be 0 u plus 6b, and the other equation for dv dt would be for u 0v. And this equilibrium, -3, 2 is a saddle. Since we've got one positive eigenvalue and one negative real eigenvalue. Any questions? Okay, then hopefully that gives you a good idea how to attack some of these homework problems if you haven't started on them Okay. Great. So I want to kind of move on into the next topic, and we'll talk about this on class on Wednesday. Your reading quiz will be somewhat related to this. So we're going to kind of take a detour from what we were looking at, and we're going to take a look back at second order differential equations and think about another method that we can use to solve second order differential equations. And this will have more universal applications for when we don't have constant coefficients. So we're going to be looking at things that might look like things that look like this, okay, where before we were looking at things that looked like using characteristic equations, etc. That method doesn't work if we have, if it's non-autonomous, if we have t's in there. And the other nice advantage of this, so we've looked at kind of calculus ways of solving differential equations, how we can use linear algebra. And here's like an analysis, real analysis sort of way of solving these. So Laplace transform is going to give us a way of taking this kind of seemingly difficult calculus problem and convert it into an algebraic problem. And so in order to do that, we need to define what's called the Laplace transform. And that depends on improper integrals. So the definition of a Laplace transform is going to depend on us being able to calculate integrals where the upper limit is infinity. So I want to just kind of review that first, and then we can talk about the definition of Laplace transform. So when we're calculating an improper integral, upper limit is infinity, we're really evaluating a limit of an integral. Since we can't evaluate something at infinity, what we could do is look at what happens when we evaluate it at larger and larger and larger values. And this might converge or this might diverge. And if the limit exists, we say it converges, and we should be able to say what specific value it converges to. If the limit does not exist, then we say the improper integral diverges. And the picture of what we're doing, so if we take a look at number one, then here's the graph of e to the minus 2t. And if we're evaluating the limit from 0 to infinity, then what we're calculating, right, is the area underneath that graph that goes all the way out to infinity. Okay, and sometimes that area might be finite, sometimes that area might be infinite, and that's going to determine whether this thing converges or diverges. So if I want to evaluate something like number one, then really what we're doing is we're calculating the limit as the upper limit n approaches infinity. And so conceptually or visually what we're doing was we're taking a look at what happens as we send n off to infinity. And so again, we just want to be careful because infinity is not a number. So we can't just plug infinity into a formula and evaluate something. So we can integrate this. I will skip the details of that, but we can integrate this using integration by substitution. And that would look like this over here if I were to evaluate that integral. So far, we really have just been thinking about this as a definite integral with two finite limits. Right, and so plugging in the upper limit, I'm going to substitute n in for t, and then I subtract the lower limit, which is when I plug 0 in for t. And so the second piece, that doesn't depend on n, so that's not going to be affected by the upper limit getting larger, but certainly the first one does depend on that. And then we need to think about, well, what happens to this as n goes to infinity? And so what happens to that expression as n gets larger and larger and larger in a positive sense?
Denominator gets really, really large, so it goes to 0.
Yeah, this is going to go to 0. And basically, we've drawn this graph up top, right? Except this is now n. So what we can see is when you take e and raise it to a really large negative number, the fact that it's negative tells us that it's going to be approaching 0. And that's great. Sometimes these limits blow up, and that's when our integral is going to diverge. And sometimes these limits behave nicely, and that's when we're going to get convergence. So in this case, this whole thing goes to 0 as n goes to infinity. So in the end, we just get 0 plus 1/2, which is 1/2. So this converges to 1/2. Okay, any questions? So that's going to be a part of all of these processes when we're trying to calculate the Laplace transform. So let me just say for the rest of the semester, we're just going to be dealing with Laplace transforms. And so we're going to kind of break it up into what is the Laplace transform, what are some really nice properties that the Laplace transform satisfies, and then what happens, how can I use these to solve differential equations? So let me just say, we're going to sidestep differential equations for maybe a day or two and just kind of build some intuition about how Laplace transforms work, and then we'll bring these two ideas together. Laplace transform of a function is defined as the integral of that function times e to the minus st as we go from 0 up to infinity. So what we start with is a function of t, and what we wind up with is a function of this variable s. So this over here, s, we're treating that like a constant when we're doing this integration stage because we're integrating with respect to t. So just be sure that what you start with depends on t, and then after you do this process, we're going to get some function which we are going to write in terms of typically we use the variable s. And then we say if these two functions satisfy this relationship, basically this relationship over here, then we call the two functions a transform pair. So I want to be sure that we're able to come up with how we can derive some of these Laplace transforms, and then ultimately we'll kind of just organize our results into a nice table so that every time we need to use a Laplace transform, we don't necessarily have to go through the whole process. So we'll kind of have like, you have a table of integrals in calculus books, we'll have a table of common Laplace transforms, but we do want to show how we can derive some of them. So that will be something you'll be expected to do on the very last exam. So let's take one that maybe is a little bit trickier than A. Let's start with B. And the question here is, let's find the Laplace transform of this function. So kind of step one would be to write out the definition. Okay, which is going to be some improper integral. So here we're taking the Laplace transform of the function t. And so I am just replacing the f of t in the definition with our function, which in this case is t. So any questions on where I got this improper integral from? And that's just how the Laplace transform is defined. Okay, so then we want to take the limit of this integral as the upper limit n approaches infinity. So now we need to integrate this. So any thoughts on how we could integrate e to the minus st times t?
Integration by parts?
Yeah, we can use integration by parts on this. Yeah, thanks for the chats. That's right. So let me just do some scratch work. Okay, and we definitely want to see this stuff when you're working on these eventually on homework. So here we can define u as t and dv as e to the minus s times t dt. And that gives us our u and v, all that stuff. So maybe people like that. So this integral, and we'll worry about the limits afterwards, would look like u times v minus the integral of v du. So any questions with my work so far? And there's a lot of negative signs to be careful about. any questions? Okay, so if you need to spend a little more time with that one, the work is there, but and so now we've integrated this. And I do think it's useful, you don't have to at this stage, to just indicate like what is the variable here, since you want to be sure you plug these in for t's and you leave the s's alone. So the s's are just treated the same as constants in this process. So when I plug in n for t, I get minus n over s e to the minus n times s and then we still need to subtract what we get when we plug in the lower limit, which is 0. So again, we're going to take 0, we plug it in over here. That's why I get a 0 over here. I take 0, I plug it in over here. So that's why I get minus 1 over s squared e to the 0 there. All right, questions? Okay, then, oops. Okay, so here's what we had, previous step. And so now, when I simplify all of this, right, we just get 1 plus s squared over here. 2 negatives give me a positive. And now when I'm calculating this limit, then let me just say,
There may be a delay, or we're not in the right screen.
I think there's just a delay. Let's see, let's give it a chance. But thanks for the warning. Okay, it's coming. Okay, so right, we've got our plus 1 over s squared over here. And I'm just going to think about each of these limits separately, since we've got 2 bits here. And so as n goes to infinity, there's only one n over here. What happens to this term? Right, so I'm seeing a 0. This is going to go to 0 for the same reason in the previous case. So this is constant, but we get a constant times 0. So that term is going to give us a 0. And then this one is more complicated because this piece over here going to 0, this piece over here, right, is going to negative infinity. So as n is getting large, one of them is going to 0, one of them is heading towards infinity, and anything can happen at this point. It depends which one is going faster. So I can write this, for example, as right, saying e to the minus ns is the same thing as saying divide by e to the n times s. And when I think about it that way, right, we get a infinity over infinity case. And what do we do when we take a limit and we've got infinity over infinity?
L'Hopital's rule.
Yeah, so this means we are going to use L'Hopital's rule here, which says we're, instead of taking the limit of this ratio, let's take the limit of the derivatives. And here we're taking, since the limit is with respect to n, we're differentiating with respect to n. And from that, we can see the top is now finite, but the bottom is still heading off towards infinity. So this is approaching 0. And you might make that observation by thinking exponential things are going to decrease to 0 faster than that linear thing is going to head towards negative infinity. So the exponential thing wins out.
Would that be adequate justification on the exam, just saying exponentials go faster to 0?
Yeah, that's okay. I think certainly writing out L'Hopital's rule is a little more complete, but if you're kind of in a time crunch, then it's okay to make that observation. Yeah. So we've got 0, minus 0, plus 1 over s squared. So all of this simplifies to 1 over s squared. So this tells me the Laplace transform of t is equal to 1 over s squared. Okay, provided that s is bigger than 0. Okay, so I will stop here. I wanted to go through one of these together, and this way it's recorded on Zoom, and so you guys can kind of go through this again if you have some questions. And this is kind of what the reading quiz will be about, thinking about improper integrals and what is a Laplace transform, but we'll get into the rest of these next time on Wednesday. Okay, and then the homework assignment relating to this material will be due after your exam.
Where did the s is greater than 0 come from?
Yeah, that's something I should explain a little bit more carefully. I just realized I'm out of time. So if people need to run somewhere, feel free to go. Yeah, I can explain that in a second. But yeah, to answer your question, that it comes from looking at these, right? Since s could be any number at this point, we're just kind of treating it as a constant. But if s were negative, then I would have something negative times something negative over here, right? A large negative number. So if s were negative, then this power actually becomes positive. And this limit wouldn't exist in that sense. This thing would converge. So this only converges provided s is a positive number. And so if s is positive, that's going to guarantee that this power is negative, and this is going to head to 0 as n gets large.
Okay, that makes sense. Thank you.
Yep.